Hi everybody, I'm the greatest living inventor, and today we are doing my invention, solitonic gravity. So let me write it down. Solitonic gravity. Like dot the I and cross the T's. Okay, so first I'll take off my jacket. Okay, so my theory is based on Lesage's theory of gravitation. Okay, so all the links will be in the video description as always. So you should read about Lesage's theory of gravitation. It's by George Louis Lesage. Lesage and by Nicolas Fatio, sorry, de Duilier. Okay, so Lesage theory of gravitation. This theory is basically considered wrong, but I think we can fix it with new concepts that were not known yet in Lesage's time. Okay, so Lesage's theory. Here is Richard Feynman's explanation from Feynman Lectures on Physics, 7-7, what is gravity? Okay, so Richard Feynman. Feynman, who explains this theory. He didn't invent it, it's just explaining it. He's a great genius in physics, and also later we will talk about Maxwell, so another like one of the most genius like Einstein and Newton in the same level, Maxwell. So I'm bringing these names so that you will see that this theory is not just another theory. It's the theory. Okay, just had problems, and we are fixing now the problems. My invention is fixing the problems. Okay, so Richard Feynman explanation from 7-7, chapter 7, section 7. What is gravity? Many mechanisms for gravitation, I'm quoting, many mechanisms for gravitation have been suggested. It is interesting to consider one of these, which many people have thought of from time to time. At first, one is quite excited and happy when he discovers it, but he soon finds that it is not correct. It was first discovered about 1750. Suppose there were many particles moving in space at a very high speed in all directions. Okay, like this way, this way, this way, this way, this way, towards you, towards me, all directions, at a very high speed in all directions, and being only slightly observed in going through matter. When they are absorbed, they give an impulse to the earth. Okay, if they hit something, they push it a little. However, since there are as many going one way as another, the impulses all balance. Okay, one pushes me from here, another pushes me from here. I'm staying in the same place. But when the sun is nearby, the particles coming towards the earth through the sun are partially absorbed. So fewer of them are coming from the sun than are coming from the other side. Okay? So if there is the sun, and there is the earth, of course it's not to scale, we are a lot smaller than the sun and a lot further away, but let's say the particles are coming. Okay, so some of them come from here, and some of them come from here, but they are stopped by the sun. Okay? So from all those that pass the sun, only one can, so it doesn't balance. So Earth is attracted towards the sun. Okay? Because most of these are absorbed, taken by the sun. Okay? So, okay, so therefore the Earth feels a net impulse towards the sun, and it does not take one long to see that it is inversely as the square of the distance, because of the variation of the solid angle that the sun subtends as we vary the distance. Okay, so if we are further away, if the distance is further away, we get a lot more of these pushes from here, because some of the pushes come like this. Okay, so if there are pushes like this, if we are close, we don't get them. If we are far away, we get them. Okay, so a small distance already makes a lot of change in the gravity. Okay, of course, there are also from here. Okay, so this balance, but the net result is that if we are a little further, we get a lot less attraction or push towards the sun. Okay, so what are the problems? Now I will explain the problems in this theory. Again, quoting from Feynman and from Maxwell, and later on I will explain my invention, which is the solutions to these problems with the mechanisms that during Maxwell's time and Lesage's time and the Dollier's time and Feynman's time and even and Maxwell's time and even Feynman's time were not so developed. Okay, so I'll explain it using new technology. Okay, so I'm erasing this. Actually, it's not new technology that I'm explaining, it's new science, the facts of science that we know. It's like basic science. It's not some technology. Okay, and these people in old ages didn't know. Okay, so problem 1, drag. What is wrong with that machinery? I'm quoting Feynman. What is wrong with that machinery? It involves, okay, what you've seen here. Why is it not correct? It involves some new consequences which are not true. This particular idea has the following trouble. The Earth is moving around the Sun. Okay, so let's look at it from above. So this is the Sun. And this is the Earth. And the Earth is moving around the Sun. Can you see the Sun? Barely. Okay, let's make the Sun brown so you can see something. Okay, this is the Sun. Yeah, better. Okay. What is wrong with this machinery? It involves some new consequences which are not true. This particular idea has the following trouble. I'm just closing the air conditioning. Okay, this particular idea has the following trouble. The Earth is moving around the Sun. The Earth, while moving around the Sun, would impinge on more particles which are coming from its forward side than from its hind side, from its back side. In parentheses, when you run in the rain, okay, you run, you get rain in your face. When you run in your rain, the rain in your face is stronger than that on the back of your head. Therefore, there would be more impulse given the Earth from the front and the Earth would feel a resistance to the motion and would be slowing up in its orbit. Okay, so you have a constant bombardment of the Earth as it's going until it stops. One can calculate how long it would take for the Earth to stop as a result of this resistance, and it would not take long enough for the Earth to still be in its orbit. So this mechanism does not work. No machinery has ever been invented that explains gravity without also predicting some other phenomenon that does not exist. Okay, so this is problem 1. Problem 2, heating. Maxwell argues that the temperature of bodies must tend to approach that at which the average kinetic energy of a molecule of the body okay, like the Earth, a molecule in the Earth, would be equal to the average kinetic energy of an ultramundane particle, okay, like what's around it. And it states that the latter quantity must be much greater than the former, okay, the particles that hit the Earth, all these particles that hit the Earth are much greater, move very fast, and the particles in the Earth are relatively not moving very fast. And concludes that ordinary matter should be incinerated within seconds under the Lesage bombardment. Okay, so this bombardment, Maxwell said, okay, Maxwell. Okay, he invented the theory of electromagnetism. Okay, so there are 4 laws of Maxwell. You should look it up. Okay, so he's in the same level of Newton and Einstein. Okay, so ordinary matter will just burn, incinerate. Okay, so this was the problem of heating. Now problem 3. The numbers of the problems are not important, but I use the numbers to explain each solution. So this is the importance, that when I will talk about the second solution, it's actually the solution to the second problem. The third solution is the solution to the third problem. Let's see what the time is. 17, almost 18 minutes. Okay. So problem 3, energy. Maxwell also argued that the theory requires an enormous expenditure of external power. Okay, what gives these particles the power to do this? Who sends them? And therefore violating the conservation of energy as the fundamental principle of nature. Okay, so again, this is Maxwell. These are big names, the biggest names. Okay, so importance of this theory. Okay, so this is again Maxwell. In spite of these problems, Maxwell wrote, "Here, then, seems to be a path leading towards an explanation of the law of gravitation, which, if it can be shown to be in other respects consistent with facts, if we solve these problems, may turn to be a royal road into the very arcana of science." Arcana is like mysteries or secrets. And Maxwell also said, "We have devoted more space to this theory than it seems to deserve because it is ingenious, and because it is the only theory of the cause of gravitation which has been so far developed as to be capable of being attacked and defended." Okay, so now I'm starting my invention. So solution 3, solitons. So I'm erasing everything. I'm starting with the third problem. So I'm answering the energy problem. Solution 3, solitons. Okay, remember the whole invention is called the soliton gravity, solitonic gravity. Solitons in water. Now I will explain what is a soliton. A soliton is a special kind of wave that acts like a particle. It continues without changing its shape and keeps its identity even when it collides with other solitons. The person who discovered the soliton was John Scott Russell in 1834. John Scott Russell. He called it wave of translation. Here is his description in his own words. I was observing the motion of a boat which was rapidly drawn along a narrow channel by a pair of horses. When the boat suddenly stopped, not so the mass of water in the channel which it had put in motion. Okay, so there is a situation like this where I'm drawing from above. Okay, there is a channel of water. Okay, so this is a long channel of water. Okay, I'm sorry, I don't know how to draw, but I'm trying to draw a channel. Okay, and this channel is in the ground. Okay, so here there is water in the channel. And here you should imagine ground, and in the back of the board also ground. And on the ground there is a boat that is in the water. Okay, let's draw the boat here. And a boat. And the boat is dragged by horses. Okay, there are horses here that are walking and they are dragging, pulling the boat. Okay, here is a horse. And it's dragging, there is a rope, and it's dragging the boat. And here is another horse, and they're dragging the boat. And once they stop, okay, the boat is moving, but suddenly they stop. But the water in front of the boat is not stopping. Okay, there is like a wave. And this wave continues. Okay, so the wave continues to go, even though the boat is stopped. The wave continues to go and it doesn't stop. Okay, so this is the soliton. This thing is the soliton. Okay, so I'm reading what he is saying. I was observing the motion of a boat which was rapidly drawn along a narrow channel by a pair of horses. When the boat suddenly stopped, not so the mass of water in the channel which it had put in motion. It accumulated round the prow, round this part, the front, upper front of the boat, of the vessel, in a state of violent agitation. Then suddenly leaving it behind, rolled forward with great velocity, assuming the form of a large solitary elevation, a rounded, smooth and well-defined heap of water. Okay, so I didn't draw it correct, it's like more smooth. And less high, but I want you to see it. Okay, it's something like this, and it's going on and on and on. Then suddenly leaving it behind, leaving the boat behind, the wave, the soliton, rolled forward with great velocity, assuming the form of a large solitary elevation, okay, just one, a rounded, smooth and well-defined heap of water, which continued its course along the channel, apparently without change of form or diminution of speed. Okay, it did not decrease its speed, it's still the same speed. Okay, I followed it on horseback. Okay, he had another horse, this man, this scientist, and he rode along the channel with another horse and overtook it. So he passed it, still rolling on at a rate of some 8 or 9 miles an hour, preserving its original figure, some 30 feet long and a foot to a foot and a half in height. Okay, so it's like this. But it's going on and on and on, it's continuing in the same speed and looks the same. Its height gradually diminished, and after a chase of 1 or 2 miles, I lost it in the windings of the channel. Okay, so the channel went not straight, so it lost energy. Such, in a month of August 1834, was my first chance interview with that singular and beautiful phenomenon, which I have called the wave of translation. Russell spent time making practical and theoretical investigation of these waves. He built wave tanks at his home and noticed some key properties. The waves are stable and can travel over large distances. Normal wave would tend to either flatten out or steepen and topple over. 2. The speed depends on the size of the wave and its width on the depth of the water. 3. Unlike normal waves, they will never merge. So a small wave is overtaken by a large one. Remember, the large one travels fast. So it just passes the little one, and they both exist separately, rather than the two combining. Another point, if a wave is too big for the depth of water, it splits into two, one big and one small. Okay, now solitons in space. This is part of my invention. Solitons don't have to travel through water. There are electromagnetic solitons. So my theory is that over a long distance there is an evolution of waves. some combine into being solitons, and only the solitons survive in the long run. Waves are forming and dispersing all through the universe, but only the solitons live long enough to reach us. So I claim that a barrage of solitons is constantly bombarding us from all directions. This solves the energy problem, problem 3, of what creates them. Okay, so this was the solution to the third problem. Now solution 2, laser cooling. Okay, solution. Two, laser cooling. Can you see the marker? Yes. Okay, laser cooling. There is a great explanation of laser cooling in this video by 60 symbols. Okay, so you should watch this specific video. 60 symbols. Laser cooling. Okay, he explains that they are, it's like the particles that we want to cool down, to make them cold, are, which means in particles means that we want them to slow down, to move slowly. So we create, it's like we use light, lasers, to make it like it's moving inside the molasses, or a trickle in British English, which is a viscous syrup. Okay, so in laser cooling we want to bring atoms to move slower and hence to be colder. Okay, so the important part in this video, why I want you to see this video specifically, is that he explains a lot this thing that if a particle is moving, okay, this is a particle, and we give it a laser in front of it. So the laser needs to be in a specific frequency, okay? This has frequency. And this needs to be in exactly the same frequency. Okay, otherwise it will not meet. They will pass by each other, okay? They have to be in the same frequency. Including effects like Doppler effects. That means if this is moving towards you, then it moves, it has higher frequency. Like you have a motorcycle and it's coming and you hear it, ignore the volume, that you hear it loud when it's here. I'm not talking about the volume, I'm talking about the pitch of the sound. The sound is higher when it's coming towards you, and the sound is lower and lower when it's going away. from you. So it's like if there is a motorcycle coming, there is like a okay, so it's like the sound is getting higher and then it's getting lower. So the frequency, if it's coming towards us, the frequency of the wave is higher. The wave, the particle, it's the same. And the laser frequency should be higher also in order to affect it, because otherwise it will not affect it. So this is explained really, really well here, so you should see this video. Okay. Now, how resonance works. How resonance works. Okay, I'm trying to explain this a little bit, why it only affects each other when it's in the same frequency that it should be. Laser cooling works because of resonance. We all know resonance from sitting in a swing as children. The natural back and forth movement of the swing has a certain frequency depending on the length of the rope. If someone pushes us a little each time in the correct timing when we fall downwards, then our speed will increase more and more and more. Okay? The push can be very gentle. A kid can push his big dad. It will still get a big amplitude eventually. The important thing is the timing, that it resonates, okay, resonance, with the natural frequency of the swing. Another classic example is that an opera singer can shatter crystal glass with her voice. How can this be? Every object has a natural frequency where it vibrates the most. When you rub your finger gently on the lip of a drinking glass made from crystal, okay, not a normal glass from the kitchen, but a special wine glass that is made of crystal. It's not every wine glass, it's special glass. You might have to wet it a little with spit. You can hear it. Here is the amazing Robert Tissot playing Dance of the Sugar Plum Fairy from the Nutcracker by Tchaikovsky. Okay, so if you want, you can see the video in YouTube. Robert Tissot. Okay, Sugar Plum Fairy by Tchaikovsky. Okay, it's just beautiful. It doesn't it doesn't add to your understanding. It's just really, really beautiful. Okay, so back to the opera singer. If the singer's high-pitched voice is tuned to the exact frequency of the glass natural vibration, it pushes the glass each time, okay, like the swing. Pushes the glass each time. The glass bends a little and then comes back, like the swing seat. And each time we push it, it's moving further. The pushes accumulate more and more until finally the glass breaks. Here is an impressive demonstration and explanation from the TV show Time Warp. Okay, Time Warp. I'm giving you all the links to the YouTubes and everything in the description of the video. Okay, laser can cool the atoms. Okay, I'm just 40 minutes, I need to hurry. Okay, so I'm erasing everything. This is still in solution 2, so I'm not erasing the title. Okay, laser can cool the atoms. Everything has its own natural resonance frequency, where it's most affected by pushes, even tiny atoms. Each atom's frequency is based also on the speed that it is moving. Okay, this is the Doppler effect, the motorcycle. So in laser cooling, we push with the radiation of laser light, like pointing a flashlight at the atom running towards us. If our laser light is tuned to the correct frequency, we will only affect this atom, and our push will slow the atom down. The other atoms are not affected because they are moving in a different speed, so they have a different frequency of resonance. Okay, if I'm shining a light, okay, let's say this is a laser, towards, let's take the red one. Okay, I'm shining towards the particle, which is coming from here. Then, because it's moving, it has a special frequency like the motorcycle. If there is a particle going away from me, it has another frequency, and this flashlight will not affect it. Okay, because I'm targeting, I chose the right frequency from that fits the particles that are coming towards me. It doesn't fit, it doesn't talk to the particles that are running away. They are not affected by it. Only the ones that are coming towards me, and they slow down. Okay. The other atoms are not affected because they are moving in a different speed. So they have a different frequency of resonance. So after we cooled the faster atoms, we use lower frequency in our laser light to slow down the slower atoms, and so on. Okay, after it's slowed down, it no longer is affected by the same frequency. I need to lower the frequency more, and so on. In this way, scientists bring materials very close to the lowest temperature possible, the absolute zero. Okay, now we talked about laser can cool the atoms. Now we are talking about solitons can cool the atoms. So, my theory claims that in the same way, solitons are tuned naturally to the correct frequency of an atom at rest. Okay, so solitons are fit exactly the rest when the particle is at rest. So this is the frequency of the solitons. So because the solitons both heated them and chilled the atoms, cooled the atoms of the Earth, of us, and so on, then we don't get hotter and hotter. Okay, so we solved the heating. This solves problem 2, heating. Okay, now solution 1, direction of movement. Solution 1, direction of movement. When the atoms are on the move, like when the Earth is going around the Sun in space, okay, so I'm drawing it again. This is the Sun. And this is the Earth. Okay, and the Earth is moving around the Sun, like so. Rotating around the Sun. When the atoms are on the move, like when the Earth is going around the Sun in space, remember the solitons are pushing each atom, so there should be a drag. Okay, remember the first problem. There should be a slowing down towards here, because they are moving towards here. It's like running in the rain, and the Earth should feel this rain of bombardment of particles. So there should be drag. But also remember that every atom's natural resonance frequency is changing because of the atom's movement. Okay, since they are moving, it's like the motorcycle. They have another frequency now. It's not like they are in rest. And the solitons only affect them if they are in rest. And the solitons are optimized naturally for the atom to be at rest. So this is why the solitons that come in front, in parentheses, solitons that arrive in a tangent direction to the Earth's orbit around the Sun, okay, like this, towards the Earth, almost don't slow the Earth down at all, because the Earth is moving towards the solitons. So the Earth's atoms are not in frequency. On the other hand, the solitons that come from the side, okay, so solitons that come through here, they don't feel the Earth at all. They just move through the Earth. But solitons that come from the side are affecting the Earth because it's not moving towards them. So from their point of view, the Earth is still. It doesn't move. Because it doesn't move to here or to here. It's just moving towards here. You understand? So from their point of view, nothing is moving towards them. So the Earth is standing still. So they are affecting the Earth. They are pushing it towards the Sun. On the other hand, the solitons that come from the side, solitons that come in a direction along the radius of the Earth's orbit around the Sun, don't see a movement of the Earth towards them or away from them. So they do affect the Earth's atom and push it towards the Sun. This push of the Earth towards the Sun is the gravity that the Sun exerts by its shadowing the solitons behind the Sun, okay, on the Earth. So there are solitons coming from here, but they are blocked, and there are solitons coming from here, and they are not blocked. So the Earth is coming towards the Sun. This push of the Earth towards the Sun is the gravity that the Sun exerts by its shadowing the solitons behind the Sun on the Earth. This solves problem 1, drag. Okay, so this was my invention. I hope it was clear, and I'll see you in my next invention. So thank you very much. Goodbye.